Hey everyone, welcome back to my channel Dr. Maths. So if you're a college student taking Calculus 2 right now, going through the topic infinite sequences and series, do not worry, you are here at the right place because I understand how challenging that can be. So today we are going to demystify that topic. We will be working through 50 problems ranging from easy foundational concepts to really advanced ones, all designed in a way that you gain a comprehensive understanding of the topic and also the skills and confidence to approach any problem in the subject itself. The best part is I'm going to give you a step-by-step solution strategy which is repeatable and you can use it on any single question in this topic. So let's get started without further delay. So here we are solving 50 problems on the topic infinite sequence and series. So before we begin, let me ask you this question. Have you ever thought about something which never stops, like it keeps going forever? And that's the heart of today's class, infinite sequences and series. The essence of the word infinite is something which is not bounded and not finite. And we want to learn now how to mathematically handle these kind of objects. So let's get started. So I've divided the entire topic in 5 parts. In part 1, we will be focusing on sequences, obviously infinite sequences, followed by terminology and some examples. So it's important to learn how sequences converge and diverge because some of the times I have seen students often neglect the importance of understanding sequences first because it's a kind of prerequisite to infinite series. So do not do that mistake. Get your concepts about sequences perfect and then only you go to infinite series. So in part 2, we'll be introducing infinite series, terminologies, definitions, and some convergence tests. More importantly, we'll be focusing on understanding the meaning of convergence first and then, of course, apply the test. Because again, I've felt students not fully understand the meaning of convergence and divergence, but they just directly somehow jump to the questions, which is not a right thing. So we'll dig deeper into that. And then followed by part 3, where we'll be talking about specific kind of series, geometric, telescopic, and positive term series. Like this further has subcategories. And believe me, this categorization is perfect. Knowing that we want to fulfill the goal of mastering a step-by-step strategy. We want to learn things in a structured manner. So when you categorize your series in this way, it gives you a hierarchy of applying the test so that you are able to complete the question successfully. So you learn that, understand that once we finish all of this. In part 4, we will be talking about another kind of series, which is alternating series, and 2 really important concepts associated with it, absolute and conditional convergence. Followed by part 5, in which we'll be looking at power series, Taylor's and Maclaurin series, and their applications. So for today video's lecture, we'll be covering only part 1, part 2, and part 3 because it's huge. It's a big concept. I do not want the lecture to be like super long. So let's just focus on 1, 2, 3 right now. And this will be covering 40 problems in total. And the remaining part 4 and part 5 will be covered soon in my next video lecture. So stay tuned for that. So let's dive in. Now again, before we begin with our part 1, I want you to know these are the target skills for today's lesson. We'll understand the meaning of convergence and divergence for both sequences and series. The difference is there's a big difference in both concepts for sequences and series. They are not same. Identify correctly the convergence tests, and of course the master step-by-step solution strategy, which of course you will do once you see me doing so many problems. You'll understand the structure, the steps it involves to correctly attack the question. So here we are, part 1, sequences. So before I read this definition to you, I want you to have a look at these examples here. So the first example of a sequence is 1, 2, 3, the very simplest possible example, and so on. These dots It means it keeps going, it never stops. So that means it's an infinite sequence. That means no matter what you do and wherever you go, how far you go in the sequence, you will be always able to find the next term in the sequence. These things are known as terms of the sequences. So in first example, the first term is 1, the second term is 2, the third term is 3. Now, if you look at this example, here the first term is 2, the second term is 4, and the third term is 6. So what we are doing basically, we are mapping the terms with numbers. We are basically counting the terms, first term, second term, third term. So you can see it as a function, that there is a function which is defined from natural numbers to real numbers, because the range of the sequence could be any real value, right? These numbers are going to be any real number. They are not necessarily rationals or integers or positive or negative. They could be any real numbers in general. So a sequence is nothing but a function, and that's the definition here. An infinite sequence of numbers is a function whose domain is the set of natural numbers or set of integers greater than or equal to some integer and not. Because sometimes for some reasons we do not start our counting from 1. We can also start our counting from 0. That this is the 0th term, this is first term, and then this is the second term. So yeah, there are various ways of doing that mapping, but most of the times by default it starts from 1, the natural number 1. So now if you understand the meaning of a sequence, so let's have a look at the general term notation for each of these examples. So what would be the general term for the first one? So you can see these are nothing but the natural numbers. So how do you define that function? So for the first example, it's an, which is the notation for the general term, equals to n. For second, it's 2n because they are all multiples of 2. For third, they are fractions, n over n plus 1. And the domains of all of these three examples is n greater than equals to 1, because n starts from 1 but it never stops. If you talk about notation, so these two commonly used notations are for sequences, the triangular bracket an or the curly braces an. So this is the notation for the sequence, and what you are writing inside that triangular bracket and curly braces, that is known as the nth term of the sequence or general term of the sequence. So of course you should be very much familiar with the terminology. So if somebody asks you what's the general term of the sequence, you should know what you're implying or what the other person is asking you to provide. So that's an, that's the definition and notation of a sequence. So if you understand that, let's go ahead. So now the question is, for a sequence, we want to always ask this question, is it convergent or is it divergent? These are the two terms we'll be talking about. So here is a definition for convergence. Again, I'm not going to give you the bookish definitions. I'm trying to explain the concepts in a way that you understand in as simple language as possible, because the goal is to understand the concept and not just to cram the definitions, right? Later on, you can, of course, try to formalize more formal definitions like epsilon delta definitions for the convergence of sequences. But for the timing, for this video lecture, it is sufficient to understand convergence using this statement. So let's read it. A sequence is said to be convergent if the terms of the sequence get closer and closer to a real number L as n increases. So that means on a real line, because all the numbers are real, so on the real line, somewhere there's going to be this number L. And if you draw the terms A1, A2, A3, A4, so you see eventually they are getting closer and closer to that number L. So in general, we can say an approaching towards that real number L, which is known as the limit of the sequence as n is increasing. Now, example to understand convergence, let's take a very simple example. Let's take an is 1 over n. Now, here is a 0. A1 is 1, A2 is 1 over 2, A3 is 1 over 3, and you can clearly see as n is increasing, all of the terms' magnitudes are going closer and closer to 0. and there's no way any term is going to surpass 0. In other words, we can say limit n goes to infinity an is 0. So basically, if you want to test whether a sequence is convergent or not, you're essentially computing limit n goes to infinity of that general term. So that's the good thing about sequences. There's only one test. There is only one way of determining whether a sequence is convergent or not. Just compute limit n goes to infinity an. If it exists, if it goes to a finite number, sequence is convergent, otherwise no. Because we are talking about this real number L, but it does not exist always. For example, there might be sequences for which there is no real number like that. That means those sequences are not convergent. So it's a conditional existence, right? So at this point of time, I hope you have realized that, okay, you should be good at limits at infinity, because that is something you have learned in Calculus 1. So if some of you do not feel confident in computing limits at infinity, then go back, read that, and then come back again, because that's something which is like really important. It's kind of a prerequisite, because every single question we are going to do, whether it's sequence or series, will involve computation of a limit at infinity. So you should be really, really good at it. So that's the meaning of convergence, that the terms are getting closer and closer to one particular number. So now you have understand the meaning of convergence. So we have the convergence test here. So convergence test is compute limit n goes to infinity an. First case, if this limit exists. Now meaning of existence is it's finite and unique. If you recall the fundamental definition of limit, so that's where it's coming from, that the limit should be finite and unique. Then only we say the sequence an is convergent or converges to L. Second possibility is if this limit does not exist, means it goes to infinity or something, then we will say the sequence is divergent. And the third possibility is that the limit is not infinite, but it's finite. However, it's not unique. In that case, also we say the sequence is divergent, but more specifically, sometimes we can call those kind of sequences oscillatory. They oscillate between more than one value. So sometimes the definition third or the case third is actually merged with case 2, because this situation is actually a situation where the limit does not exist. So do not think in the third case limit is existing. Limit is still non-existent, but it's a specific type of non-existent, that it's non-existing because it's not unique. It's not non-existing because it's infinite. It's finite but not unique. So whatever be the case, only in this case sequence is said to be the convergent sequence, otherwise divergent. You don't want to go into details of whether it's oscillatory or not. Just focus on convergent or divergent. So now you have got the test. Now let's apply this test to various examples and see what we get. So the first example of the sequence which we are going to test is an is square root n. So let's compute limit n goes to infinity for this sequence. Limit n goes to infinity, square root n, very easy, it goes to infinity. So clearly limit does not exist. So by the definition of convergence, we get that this particular sequence is actually a divergent sequence. So very simple, just compute limit at infinity, boom, you get the answer. Now you can also visualize this thing in the form of a function. So if you see the function fn is square root of n, if you want to draw the graph of it, so you will see how does it look like. So it's like a forever increasing function, never settle downs. So that means if n keeps on increasing, function value keeps on increasing. So you won't see convergence happening. So actually the function value will start becoming bigger and bigger as n starts becoming bigger and bigger. That's the reason it is divergent. But yeah, so visual understanding or intuitively looking at the graph can help you understand the behavior of the terms of the sequence, but a test needs to be performed to actually know whether the sequence is convergent or divergent, because sometimes we can have these kind of situations where it might look like from the graph that the sequence is not convergent, but it actually turns out to be convergent. So do not just rely on a graph of the function, but also of course perform the test, which is like compute limit n goes to infinity. That's the only way you are going to do it. So we are done with the first example. Let's move to example number 2. Again, a very simple example, 1 over n. Now, in this case, of course, if you compute limit n goes to infinity, it's very easy to see that this limit is equals to 0. Now, this is a finite and unique number. So by the definition of convergence, this sequence turns out to be convergent, and this converges to 0. Because in this case, we have that information, okay, sequence is convergent, but where it is converging. So whatever you have found as the limit, that is where sequence is converging. So that means infinitely many terms of the sequence are going to be very, very close to 0 when n is very, very large. That's a way to look at it. All right, let's move to example 3. So this factor -1 to the power n is actually quite common in sequences and series. So you need to understand what does it do. So this is a function which takes only two values, -1 or +1. So whenever the power is going to be odd, it returns a -1, and if the power is even, it returns +1. So it's kind of gives you an oscillatory behavior, and the terms are alternatively negative and positive. Like if you write down the terms of this sequence, so the very first term is going to be -1 to the power 1 over 1. Second term, -1 to the power 2 over 2. Third term, -1 to the power 3 over 3, and so on. And when you simplify, you get the first term is -1, the second term is 1 over 2, the third term is -1 over 3, and so on. So the terms are alternatively positive and negative. So that's why this factor is known as alternating factor. So let's see how does it affect the convergence for this sequence. So we are going to follow the same process. So you write down the general term, compute limit n goes to infinity of -1 to the power n over n. I can divide this in two parts. So clearly this factor is oscillating between -1 and 1. And the other term, this limit goes to 0. So overall it goes to 0. So this sequence is actually convergent, and it converges to 0. So that means the presence of this oscillatory factor between -1 and 1 did not change anything. This sequence is still converging to 0. But take care, that's not always going to happen. Sometimes there can be other instances. For example, let's have a look at this example. Example 4, where we have -1 to the power n plus 1. Now in this case, of course, if you try to compute limit n goes to infinity, then we know that this is going to take only two values, -1 if n is even and 1 if n is odd. So clearly it's never going to reach a unique limit. Therefore, this sequence is an oscillatory sequence, or you can say this is a divergent sequence. In other words, you can say it is not convergent. So this is how it is different than the previous example. More specifically, if you want to call it oscillatory, you can do that. But that's a term not used by, I would say, many of the authors. They want to just call them divergent, even if they are oscillatory. So it's up to you whether you want to learn that terminology or not. That's like optional thing for you. So here we are, already did 4 examples for the sequences. Let's move on to the next example. Again, a very simple example, an equals to 3. Now, what kind of sequence it is? It's a constant sequence. So if you look at the terms of the sequence, so it's going to be like 3, 3, 3. It's like a constant function, right? So it never goes anywhere. It stays at 3. So very easy. If you compute the limit of this sequence or the general term, so you know what it is going to be. It's going to be the number 3 itself, which is finite and unique. Hence, this is a convergent sequence and it converges to 3. So you note that every constant sequence is always convergent and it always converges to the number itself. So easy. So you can remember this. Constant sequence, you don't even need to test it. It always converges to the same number. Let's have a look at example number 6. Again, repeating the same test. So let's compute now limit n goes to infinity 3n plus 1 over n plus 1. Now you need to recall from the calculus 1, how do we compute this kind of limit? So we are going to divide with n in the numerator and the denominator, because then 1 over n, that will go to 0 and you will be able to simplify. So you can see it goes to 3. So this is a sequence which goes to 3. So what I want you to do when you're going through these slides and examples, you can draw these functions graphs maybe in Desmos and you can see the behavior of the functions. So you will find the terms or the function approaching towards 3. It's like a horizontal asymptote if you remember from calculus. So, okay, here we got the answer, convergent, and converges to 3. Example number 7. Okay, so here we bring a trigonometric function cosine n divided by n. Now we want to, of course, compute the limit n goes to infinity cos n over n. So it's not easy to compute. So if you recall squeeze theorem or sandwich principle, we can use that here. Cos n lies between -1 and 1, dividing with n, and then computing the limits of the extreme functions, which in this case, both of them are going to 0. Thus, by squeeze principle, the middle function also goes to 0. Hence, it is a convergent sequence. So you see, it's just a practice of, again, computing the limits at infinity, which we have already done. They're just appearing here as a term of a sequence, but they are nothing but the function of n only. So this also turns out to be convergent. Next example, example number 8, it's n to the power 1 over n. So now if you try to directly substitute infinity in this case, it will give you an indeterminate form, which is infinity to the power 0. So we remember for indeterminate form, we have to do certain kind of treatments. So let's take log here to bring the power down. And then after taking natural log, you take limit n goes to infinity. Now in this case, it is again indeterminate, infinity over infinity. But if you use L'Hopital's rule, you will see it is 0. But an will be e to the power 0, which is 1. Thus, this limit is actually equals to 1. So this is one of the standard limits which appears so frequently in the whole chapter of sequences and series. So you can remember it. Instead of computing it every time and doing all these steps, you can remember this, that this limit is going to be equals to 1. I skipped the steps here, but I can show you how we got 0 here. So infinity over infinity, that will be the first indeterminate form you get when you directly substitute n goes to infinity. And then you use L'Hopital's rule. So ln n over n, so the derivative above will be 1 over n, the derivative below will be 1. So it will reduce to 1 over n, which will go to 0 eventually when n goes to infinity. And this was the limit of natural log of an, but we want the limit of an, so that has to be e to the power 0, which is equals to 1. So that's how you get this limit and a sequence which is convergent. Here we have another standard limit which appears like quite frequently again in not only in sequences but series. So I'm not going to show you, I would say, the whole proof of this, that why this is equal to that particular value. I'm going to give you a standard limit to remember. So again, in this case, if you try to compute limit n goes to infinity first, you will get indeterminate form. But here we have this result which will help you to remember this limit. So any limit of this kind, limit n goes to infinity, 1 plus x over n to the power n, it's actually e to the power x, where x is any fixed real number. So whenever you see this kind of function, you just know the limit. So our case, limit n goes to infinity, 1 plus 2 over n to the power n will be actually e to the power 2. Because of x, in place of x we have 2 here. Clearly, which is finite and unique. Thus, therefore, this sequence is also convergent and it converges to the limit e square. So it's helpful to remember this limit because of this kind of functions appearing many times. For example, if you will have limit n goes to infinity, 1 minus 1 over n to the power n. This is actually going to be equal to e to the power negative 1. So you just have to read the number here, which is at the numerator of n here. It could be positive, it could be negative. Whatever it is, raise it to the power of e. That's going to be the value of the limit. So remember this, it's going to be helpful. All right, next example. So let's include log function now, natural log function. So this is my sequence general term given to me. Now in this case, of course, if you try to compute limit n goes to infinity, ln n over n to the power 1 over n, then we just learned that the denominator limit n goes to infinity, n to the power 1 over n is actually equals to 1. I just shown you that's a standard limit. So you can use that here. And it's only this function now, which of course goes to infinity. Thus, the given sequence is a divergent sequence. So through this example, you learned that knowing some standard limits help. Otherwise, the calculations would have been lengthier. You would have to compute that limit separately by taking the logs, the way we did it in example number 8. So here you just use that directly and simply get your answer. So here we are. These 10 examples were focusing on part 1 sequences, and you saw that all of them required only one test. Limit at infinity. If that limit exists, finite and unique, convergent, otherwise divergent. As simple as that. So now we want to move to part 2, which is infinite series. So let's first understand the meaning of an infinite series. Let's have a look at this example, 1 plus 2 plus 3 and so on. This is an infinite sum known as a series. 2 plus 4 plus 6, again an infinite series because it keeps going on. 1 plus 1 over 2, 1 over 2 square plus 1 over 2 cube, that's again an infinite series. So in general, this is how a series look like, a1 plus a2 plus a3 and keeps going. And this is a sigma notation, n equals to 1 to infinity, also known as summation. So this is an infinite series. This is known as expanded form of the series. And the other side is known as the compact form of the series. So the compact notation is the one which is more commonly used because the expanded form is not really useful when we are testing the convergence. So obviously we'll be given this kind of questions. Now, if you distinguish between a sequence and a series, so you could recall now the definition of a sequence. Sequence was like 1, 2, 3. So the terms were separated by commas. 2, 4, 6. The terms were separated by commas, but here the terms are added up. So it's actually a giant sum. It's just one single big mathematical expression where you do not have end to the numbers which you are keep adding to that expression, right? So this is an infinite sum. So precisely it's a sum, but it's given the term infinite series. So that's the first thing. You should know the difference between a sequence and a series. Had it been a1, comma, a2, comma, a3, so this is a sequence. But if it looks like a1 plus a2 plus a3 and so on, this is a series. Both of them are infinite. And the summation notation obviously distinguishes it from a sequence. Sequence notation was this triangular bracket or the curly bracket, while series is summation. So these two are sequence notation, but for series we have this particular notation. So you understand the meaning of series now and how it's different than a sequence. So since it's different than a sequence, its convergence is going to be having a different meaning, altogether different meaning than what we meant by convergence of a sequence. So let's understand convergence of a series. So the first point is the same thing which I just said. Convergence of a sequence is not same as convergence of a series because there are two different mathematical objects. Now convergence of series mean that if you keep on adding these infinitely many numbers, it should end up to a finite value. The sum should be a finite number. So that means if this series is equals to finite number, the sum of all the terms is finite number, then only we say the series is convergent. Otherwise we say the series is divergent. Example to understand this could be, say you have, let's take a very simple example, 1 plus 1 plus 1 and so on. So you clearly see that it's not a finite number. If you keep adding 1 to itself infinitely many times, it's never going to settle down to a finite value. So that's why it's an example of a divergent series, which gives us our first result. Every constant series is always a divergent series. Summation an, where an is a constant a, where that is a non-zero number, then it diverges. Of course, if it is 0, then it's not going to diverge because 0 plus 0 plus 0, that is a finite number. You keep adding 0 to itself infinitely many times, it definitely gives you a finite number. So summation 0 is convergent, but everything other than 0, if there's a constant, it's divergent. So you recall we talked about constant sequence. Constant sequence was always convergent, while constant series is always divergent because of this characteristic. So the goal is, if you are able to get a finite number in the end, then it is convergent, otherwise no. Now the problem with this definition, or I would say the limitation of this definition, is it's very difficult to test. There are no suitable or easy mathematical techniques which can tell us how to compute the sum of infinitely many numbers, because all of us know how to add finitely many numbers. If we have 1,000 numbers, we can use a calculator or write a computer program for the same. But no computer program, no human being can ever find the sum of infinitely many terms. So there are no direct techniques available to do that. That is the reason we need some different kind of tests for checking whether the series is convergent or not. So there are many tests for checking whether the series is convergent or not. And this really depends on what type of series is given to you. So the important learning point in this whole journey of series is going to be recognizing the type of series which is given to you. So that's going to be your step number 1. That do you recognize a series to be of a particular type? And then if you recognize, then use a particular test. Now if that test works means if it gives you a final answer that your series is convergent or divergent, then of course you stop. But if a test which you are using fails or is inconclusive, that's the another term we use, then we have to use another test. So you can never end your question at, okay, I do not know the answer, it may be convergent, may be divergent. You always have to think about using some other test if one test fails. So if you take care of these steps, you will be able to do these questions. But yeah, the skill is to learn how to recognize what kind of series we are given. So I have planned the examples in a structured way so that it gives you the idea of that entire thinking process, and you should be able to do that in an efficient manner. So now you see the level of difficulty. Why sequences was easy and series is difficult? Because in sequences there was just one test, while for series there are like a plenty of number of tests depending upon what kind of test you are, what kind of series you are looking at. So the very first test we are going to talk about is nth term divergence test. So it's clear from the name of the test that this is a divergence test. Now what does that mean? That means that you can never imply that a series is convergent using this test. The only conclusion, if this test works, is going to be the series is divergent. Otherwise, the conclusion would be we do not know, right? So I hope you understand that. So let's read the statement of this test first. So to understand the statement of this test, we need to actually understand a theorem, which tells us if summation an is a convergent series, then limit n goes to infinity, an has to be 0. Now, if you rephrase this statement, rephrase this theorem, we can rewrite it equivalently as if limit n goes to infinity, an is non-zero, then this series is divergent. So this test is known as nth term divergence test. So the steps are going to be you compute limit n goes to infinity an. If it is 0, then you if it is non-zero, then you say it's divergent. But if it is 0, then you cannot actually say anything. So you have to use some other test to determine whether the given series is convergent or divergent. So that's the summary of nth term test. So let's try to understand why it is so, because I'm not going to give you a formal proof of this theorem, but we can just intuitively understand the idea behind it. So we are saying for a series to be convergent, this has to happen. See, what you are doing is you have infinitely many terms adding up. You keep on adding, it keeps on going. So because convergence means that in the end, it should be not a very big number. It should be a finite number. It could be a big number, but it should be finite. It cannot be infinity. Now, if you want something to be finite, it can only be possible if the terms which you are adding, an, and then after a few steps, you add a k, some kth term. So the subsequent terms which you keep on adding should be of really, really small magnitude. If you keep adding big numbers to already big numbers, it will keep increasing, right? The sum is going to keep rising. So since you want things to settle down at finite magnitudes, that means whatever you're adding, that has to be of a really small magnitude. That's the meaning of the limit n goes to infinity, an has to be 0. And so if limit is non-zero, then this is a divergent series. So we will be using this theorem in this form because that is practical for the questions. We cannot use the theorem in this form because this starts from the condition if series is convergent. That is something which is not known to us. What can be known to us is what's the limit. So we'll compute the limit. If limit is non-zero, then divergent. If limit is 0, then cannot say anything. So let's look at some examples which demonstrate the usage of this test. And let me tell you something more about this test, that this is a universal test. That means it can be applied to any series type, no matter what type it is. It's not specific to any category. It's a universal test. So you can basically use it as the very first step. Whenever you are given a series, always think of, okay, can I use nth term test? Because this will eliminate the possibility of, looking at maybe using some more complex tests. Sometimes our answers are simply found by nth term test. So that's what you have to practice now. So here we have the first example, which is example number 11 in total because we finished 10 examples of sequences, but the first example in this case of nth term divergence test. So let's take this series 0 to infinity cos n pi. So an is cos n pi. So compute limit n goes to infinity an. And this actually cos n pi is -1 to the power n. which is non-zero, because we know that this is again the same factor which oscillates between -1 and 1. So since the limit is non-zero, therefore by nth term divergence test, the given series cos n pi summation diverges. N is 0 to infinity. Yeah, so you see how simple was that? We used nth term test. So this process might be a little confusing with what we did for sequences. So you can ask here, okay, we were doing the same thing with the sequence. Even for sequences, we were computing limit n goes to infinity of an. But the interpretations were different in that case. For sequences, it was if limit n goes to infinity, an is finite or does not exist, right? So for sequences, this was the situation. So finite means convergent, does not exist means divergent. But for series, we are not looking at the limit being finite or non-existent. We are only comparing it with being 0 and non-zero. So non-zero means divergent, 0 means nothing. 0 means we need to further test it. In this case, since this is non-zero, we got our answer quickly. All right, so let's have another example of nth term divergence test. So we have this series ln n over 2n plus 1. Now if you compute limit n goes to infinity for this, and now it's easy to see that if you divide inside with n, this is what you will get, and it will be ln 1 over 2, which is minus ln 2, which is something non-zero. Thus, again, by nth term test, this series is also a divergent series because nth limit goes to something non-zero. See, we are not bothered by wherever it goes, whatever be the limit. That limit has nothing to do in deciding something. The only thing which is a deciding factor is whether it's 0 or non-zero, right? So do not try to imply anything that, okay, this magnitude means something. This does not mean anything in this context, right? So this is also an example of a divergent series. Here we have another example. N equals to 0 to infinity, e to the power n over n. Now in this case, if I take limit n goes to infinity, so of course you'll get infinity over infinity first, which is an indeterminate form. So you take the derivative above and below, so eventually it goes to infinity. So infinity is something which is non-zero. Therefore, this is also divergent. We are only comparing with 0. So this is also a divergent series. Here we have one more example to demonstrate that this test is inconclusive sometimes, because the 3 examples we just did, in all of them we were getting divergence, divergence, divergence. But here we have an example where the test is going to fail, means inconclusive. So 1 over n, very simple example. Now in this case, of course, if you compute limit n goes to infinity, 1 over n, it's 0. Now when the limit is 0, that means you cannot say anything. That means you have to use some other test to identify whether this series is convergent or divergent. This is the exact wording you are going to write. Use some other test. Since right now we do not know any of the other tests, so we'll come back later to this example. And actually this is one of the important series, harmonic series. It has got a specific name. So we'll come back to this and know whether it's actually convergent or divergent, but this test is unable to give us information about that. So that's what when we say the test fails, it doesn't mean the test is wrong. It just simply means it cannot be applied to this example. It's inconclusive. And here we have an example where it's difficult to apply test. So I'm not saying it fails. I'm trying to show you an example where we are trying to compute limit n goes to infinity an, but maybe its computation takes so much of time and it's challenging enough that we eventually leave it and say, okay, then I'm going to use some other test. So even if we know that this test might work, but still we are not able to do it because of the complicacy of an. So here we have that kind of example. 4 to the power n plus 1 factorial divided by 3n minus 2 factorial. Now in this case, if you try to compute limit n goes to infinity, so I would say this is difficult or time consuming. Maybe you can give it 1 or 2 steps and then see, no, it's complicated. So it might be challenging actually to find this limit. So in that case, also sometimes we can say use some other test. So you see the practicality is, okay, you can use it, but only when it is efficient. If you will spend, suppose, so much time on getting this limit and suppose it turns out to be 0 in the end, so you'll say, okay, it's inconclusive. Nobody knows what it turns out to be. I'm not saying this is not possible. You can actually find this limit, but sometimes you have to manage with the how much time you have to attempt that question, and maybe you have better test available which can solve this quickly as compared to this test. So we'll come back to this kind of example later as well. So you see in nth term test, we had like 3 kinds of examples in which we were getting an answer, in which we were not getting an answer. And here we just simply chose not to use this test because it's difficult. So that finishes part 2. So I hope you understand now the meaning of infinite series, the meaning of its convergence and divergence, and the general nth term test. Now part 3 is about particularly focusing on these 3 categories of series: geometric, telescopic, and telescopic and positive term series. So the very first series we are going to talk about is geometric series. So a series of the type A, AR square, and so on is a geometric series. Actually it should be plus, not a sequence. We are not looking at a sequence, we are looking at a series. So it's A plus AR plus AR square and so on. That is a geometric series where A is actually the first term and R is said to be the common multiplier. So you see the pattern, you're starting from a term and every term you are getting by multiplying with R. So R is something whose power is increasing while A is staying there just as a multiple. To understand this, you can have these examples. So you start from 1 and maybe the multiplier you choose is 2. So 1 plus 2 square plus 2 cube and so on. So in this case, A is 1 and R is 2. Then maybe you start from 1 over 3 and the multiplier you choose is also 1 over 3. So 1 over 3 square, 1 over 3 cube and so on. So in this case, A is 1 and R is 1 over 3. You start from -1 and the multiplier you choose is -4. A is -1, R is -4. So every time you get another term by multiplying with -4. So -1 times -4 will give me +4. So +4 times -4 will give me -16. So that's -4 square. And then multiplying with another negative would make it positive, but 4 cube and so on. So this is like an alternating series, alternatively positive, negative, but still a geometric series. So all of these are example of geometric series. Now, if you understand the meaning, now the question is, how do we test the convergence of a geometric series? When does this kind of series converge? So the test for convergence of geometric series is that this series converges if and only if absolute value of R is less than 1. In other words, the magnitude of multiplier should be less than 1. If it is greater than 1 or equals to 1, then the series diverges. For example, if you have summation n is 0 to infinity 2 to the power n, this is divergent because in this case your multiplier is 2. Its magnitude is greater than 1. So this is the general way of writing or representing any geometric series. So this is like a recognition that you will see power of n raised to some real number, could be positive or negative, and some multiplier. Now in this case, you don't have any multiplier, means nothing is written here. So it's like 1. A is 1 here, but your multiplier is R equals to 2. So A has nothing to do with convergence. The only parameter which has something to decide about convergence is this R. So its magnitude should be less than 1, otherwise it is divergent. So now let's apply this to examples. Okay, before doing examples, let's talk about sum of a geometric series. So remember in the beginning, I told you that it's mathematically not always easy to find sum of the series. Even if for series, we would be knowing if it is convergent, but in most of the cases, we won't be knowing what's the sum of the series. Like for any general series, even if you know this is convergent, but knowing exactly what it converges to is another set of challenge, right? It's another task which we are not doing right now. But yeah, for geometric series, finding the sum is relatively easier. Like we have formulas for that. So for only geometric series, we can find a sum, not for rest of the series. Like we'll be able to find it even for one more type, but not in general, I must say. So this is also used as a hint by a student. Like whenever they see a question, the question doesn't mention the term it's a geometric series. They just say, okay, find whether the series is convergent or divergent, and if it converges, find its sum. So whenever they ask you to find sum, the hint is like, okay, it's more likely geometric series because that's the only series we know how to find sum of. So you get a hint, and so you compare your series with the geometric series type and get the answer. So that's the formula. So if a series ARn, n is 0 to infinity, converges, means the geometric series converges, then the sum of this series is actually equals to A over 1 minus R. Important point here is convergent. It should be convergent because it's meaningless to talk about sum of a divergent series. So if you find out that series is divergent, but if you still accidentally use this formula and say this is the sum of the series, in that case you are doing something wrong. So that's not what we are going to do. The first condition is it should be converging, only then you can find its sum. So now let's have an example of geometric series here. So an is summation n is 0 to infinity 5 over 4 to the power n. So when you compare this series with the structure a r to the power n is 0 to infinity, you can see a is 5 and r is 1 over 4. Now magnitude of r is less than 1, therefore this series actually is a convergent series. So that's what you have to do. When you recognize, find a and r. And in this case, sum can also be found, a over 1 minus r. So you simplify that, 20 over 3. So what are the steps? Recognize it's a geometric series. Once you recognize, identify what's a and what's r. To decide about convergence, you just need to know r. And while for finding the sum of the series, like if the question asks you to find sum, in case it is convergent, then this is the formula which you have to use. So this was an easy example. Let's have a look at another example. Summation n is 0 to infinity, negative 1 to the power n, 3 to the power n over 2. Now in this case, an is this whole term. If you now compare it with ARN, so it's easy to see that A is 1 over 2 and R is negative 1 and positive 3. It's minus 3. So magnitude of minus 3 is greater than 1. Therefore, this series is divergent. So clearly you could see here, this was the term which was present without anything in the exponent. So that's why that was with the constant term, not the constant multiplier, but the first term. But these were the terms which were with the power n. So both of them go into r. So sometimes in expressions, you will have multiple terms raised to the power n. So you combine them together as a common multiplier, then you get the value of r. So in this case, this is a divergent series. That's it. Question finishes there only. You don't need to do anything else. Another example. Say you have 5 over 2n plus 1 over 3 to the power n. Now I'm going to split this in actually two series, different series, because this given series is not a geometric series, but it's actually sum of two different series which are geometric series. So I individually can test them now. Now for the first case, an 5 over 2 to the power n and bn is 1 over 3 to the power n. For the first series, its r is 1 over 2, so it's convergent. For the second case, it's 1 over 3, which is less than 1 again, so it's convergent. So individually, they are convergent. Hence, the sum an plus bn is also convergent. So this is actually a result in series, which says sum of two convergent series is also convergent. Like we did this example on geometric series because I wanted to also demonstrate this result for you, that sum of two convergent series is convergent. So this is like a good practice to know that sometimes you can also split the series in multiple series and check their individual convergence first, because if individually they look like one type, like in this case both of these were geometric type and we know how to test the geometric series convergence. So you broke them up into two series further, individually find they are convergent, and using this result you conclude that this is also a convergent series. So this one is not only applicable to geometric series, this is applicable to any two types of series. So take care of that. Let's move to next example. So now you have a different kind of examples which involves a variable x over 2 to the power n, and the question is for what values of x this series converges. Now r is x over 2. We know that convergence condition is this should be less than 1. So when you simplify that, this turns out to be this. And in this case, if you want to find the sum, so sum is a over 1 minus r. Now how will you find a? It starts from 1. A is x over 2 raised to power 1. And r is also x over 2. Simplify that. You will get x over 2 minus x as the sum of the series. So this was like an indirect question. So you find r first and then use the condition, and then use the condition of convergence, that for the series to be convergent, just give me a second. For the series to be convergent, we know mod of r should be less than 1. So this eventually is going to give you an absolute value inequality to solve, which you should be knowing how to solve, and this comes in the form of an interval. So that's actually an example of a kind of question. We are going to doing it more detail in power series, but here since this was connected with geometric series, so I introduced that question here. So we are going to have a look at these kind of questions in much more detail later on. So that was all about geometric series. So the next term we want to talk about is a very important term in infinite series. It's known as sequence of partial sums. So let's try to understand what it is first. So you are given a series, summation an. Now, how do we define the following sequence? We are defining a sequence here. S1 is the first term, A1. S2 is A1 plus A2. S3 is A1 plus A2 plus A3, and so on. Sn is A1 plus A2 plus A3, and so on, An. So this Sn is the sum of first n terms of the series. And the sequence Sn is known as sequence of partial sums of the series. Now result is that the given series converges if and only if the sequence of partial sums converges. And the value of sum of the series is actually same as the limit of the sequence of partial sums, which is the sum of the series. So this is like the very first theorem which is taught to anyone whenever you are going to make a transition from sequence to series. This is actually taught even before geometric series. But since I didn't give you the proof of the geometric series convergence test, that's why we didn't need this result before. But that proof is based on this result. So what we are doing using the given series, we are defining another sequence which is coming from the terms of the series only. So first term of that sequence is the first term of the series itself. Second term is the sum of first two terms. Third term is the sum of first three terms, and nth term is the sum of first n terms. That's why it's known as sequence of partial sums, because you are partially taking a few terms at a time and adding them up. Now this sequence S1, S2, S3 and so on is known as the sequence of partial sums. So the important result is this, which we are going to use in our next kind of examples, that to test the convergence of a series, it is sufficient to test the convergence of the sequence of partial sums. If that sequence converges, then the series also converges. And more importantly, whatever will be the limit of that sequence, that is going to be sum of the series. So I just told you that it's possible to find sum of the series for a geometric series, and now we'll look at another kind of series for which it is also possible to find sum of the series. So this another kind of series is known as telescopic series. So now we are going to use a different technique, demonstrate the technique of finding sequence of partial sums. So for that we have to break this nth term. We have to rewrite this in a different form. So I'm going to rewrite 1 over n times n plus 1 actually as 1 over n minus 1 over n plus 1 as a difference of two fractions. So how do we know that it is equal to this? So to determine that, we have to use method of partial fractions, which is actually a very famous technique. You might have seen this already in integrals. If you haven't, then you will find it in any integral textbook. So read that from there and then practice it here. So what you have to do is to suppose this is equals to a over n plus b over n plus 1, and then simplify that the way you just add fractions an plus 1 plus bn over n times n plus 1. Left hand side is still the same. Simplify the numerator an plus 1 plus bn over n plus 1. And now you can see the denominator getting cancelled out. And now you rewrite the numerator as 1 equals to a plus b times n. Okay, it should be a, not 1. And now if you equate the expressions on both sides, in other words, you equate the coefficients on both sides, what you see is a plus b equals to 0. Because there is no n term on left hand side, so it's 0 times n. And a is 1. B is minus a is minus 1. So you get a is 1 and b is minus 1. Now find sequence of partial sums. S1 by definition is a1. So you plug in n equals to 1, you get this. 1 minus 1 over 2, which is left as such. You do not simplify this. S2 is a1 plus a2. A1 you just obtained 1 minus 1 over 2. A2 is 1 over 2 minus 1 over 3. S3 is 1 minus 1 over 2 plus 1 over 2 minus 1 over 3 plus 1 over 3 minus 1 over 4. And in general, Sn is going to look like this. It follows the same pattern. And last term is going to be 1 over n minus 1 over n plus 1. Now you see these terms getting cancelled out, and Sn is simply 1 minus 1 over n plus 1. If you find its limit n goes to infinity, it's easy to see this is 1. Hence, you can say the sequence of partial sums converges to 1. And by the result we just saw, the series also converges. And actually, the series also converges. The sum of the series is equals to also 1, which is the same as the limit of the sequence. So that was a demonstration of how telescopic series work. You use always the method of partial fractions in this to get an expression like this, and then write the terms of sequence of partial sums. The goal is do not simplify, because if you simplify them, then you won't be able to make that pattern. Also, do not cancel the terms here. If you cancel them here, again, you won't be able to see the pattern. So it's better you write the Sn first and then do the simplification. And once you have Sn in a simplified form, you will be able to get this. The reason why we are using method of partial fraction is because if you do not do this step and directly from here keep writing S1, S2, S3, then you won't be able to see a pattern. You won't be able to see Sn in a simplified form. That's why we need to break it down into fractions so that we see this kind of behavior. So it's like a very clever technique. But that's what it is. And you see, we got that the series is convergent. Here we have one more example of telescopic series. Summation n is 1 to infinity 4 over 4n minus 3 times 4n plus 1. Now I'm going to rewrite this as a sum of two different fractions. I'm going to again use method of partial fractions. I've already done it and written it here. You can verify it yourself. This is what it is going to be equals to. Now S1 is 1 over 4 minus 3 minus 1 over 4 plus 1. 1 over 1 minus 1 over 5. 1 minus 1 over 5. S2 is 1 minus 1 over 5 plus 1 over, now you plug in n equals to 2 there. 4 times 2 plus 1. So 1 minus 1 over 5 plus 1 over 5 minus 1 over 9. So you see they are same. And Sn is going to 5, 1 over 5 minus 1 over 9 and so on. It's the same expression which you got for An. And now these middle terms gets cancelled out. You will be left with 1 minus 1 over 4n plus 1. And clearly limit n goes to infinity for the same is going to be 1. Thus, this sequence actually also converges to 1. So coincidentally, this one is also going to 1, but there's nothing like every sequence is always going to 1 in these examples. So the given series is also convergent. I'm sorry, my pen is behaving a little weird here. The given series also converges, and the sum of that series is actually equals to 1. So this technique requires understanding of method of partial fractions. So I hope you get this one. Now let's have a look at one more example of telescopic series, which is actually not a telescopic series. So sometimes what happens, you try the just discussed technique, but it doesn't turn out to work well for you. In that case, you have to drop the idea and use some other test. So let's see that kind of example. N is 1 to infinity, ln 2n over 3n plus 1. Now in this case, if I use the property of the log, that it is equal to log 2n minus log 3n plus 1, and now I can write S1 as A1, which is ln 2 minus ln 4. S2 is A1 plus A2, so you copy and paste what you got for A1, ln 2 minus ln 4, plus A2 is ln 4 minus ln 7. S3 is A1 plus A2 plus A3, so you first copy and paste what you got for A1 and A2, which is simply S2, and then last term would be 6 minus ln 10. So here only you see they are not going to get cancelled out, right? They're not same in magnitude, hence they won't cancel out, hence you won't get that pattern, what you're looking for. So sometimes just writing 3 or 4 terms gives you the idea. So this is not a telescopic series. So that means there's no reason of continuing with the process. It simply suggests that use some other test to identify whether this series is convergent or divergent. So let's try another term test here. So limit n goes to infinity, ln 2n over 3n plus 1 is ln, again you can divide by n inside 2 over 3 plus 1 over n, which actually turns out to be 2 over 3, which is non-zero. Non-zero means divergent. So you see, one test failed, or we were unable to apply method of partial fractions. So we went back to nth term test and we got our answer. So had this clicked to you earlier, like before trying for telescopic, if you would have used nth term test earlier before than that, then you could have saved time. But it's all a matter of how you are looking at the question and how you are trying to do it sometimes. Right, so now let's move on to the next category, positive term series. So we have many tests into this category. Cauchy's integral test, specifically known as integral test, comparison test, ratio test, root test, p-series test. But what is a positive term series? We should be knowing that first. It's clear from the name though. So a series in which all the terms are positive. So an is greater than 0. That series is called a positive term series or positive valued series, or because an is a positive valued function. Examples: summation 2 over n, 4n square plus 5, e to the power n plus 4n, half 5n, all of these are positive term. But if you look at the negative 1 to the power n over n plus 1, it's not a positive term series, clearly because the terms are alternatively positive and negative. Remember, we talked about this, that whenever you have this factor present, it will have alternatively positive negative terms. You can see by expanding the terms. So if n starts from, say, 1 to infinity, so the very first term is going to be negative 1 to the power 1, which is minus. So minus 1 over 2. The second term is positive term, which is 1 over 2 plus 1, 3. Then minus 1 over 4 plus 1 over 5. So this kind of series will be handled in part 4. It's called alternating series. But other types, like all these in which all the terms are positive, they are handled now. Depending on what type it is, we'll be using an appropriate test. So we'll be going through all of these 5 tests one by one and see what are their statements and when to use which one. So the first test we are going to talk about is integral test. So the statement is this: let an be a sequence of positive terms. So that's the first condition, as we said, positive. And suppose an is fn, where f is a continuous, positive, and decreasing function. Decreasing is important here, of x for all x greater than equals to n, where capital N is a positive integer. In that case, summation an, this series, and the integral fx dx behave alike. Both behave alike. What do you mean by behave alike? Means they converge or diverge together. So continuous, positive, and decreasing, these are the 3 conditions. Continuous will be like default satisfied. Usually we do not need to test the continuity because most of the functions are by default continuous. Positive is also like by default satisfied. Again, no need to test it. If not positive, we can clearly identify, then of course we'll use some other test. However, if you want to check the decreasing part, then for that you need to actually prove or test it explicitly whether it's a decreasing series or not, like the terms are forming a decreasing sequence or not. Because if that does not happen, then you cannot use this test, because that's like one of the conditions. The function must be satisfying. So what this test is actually doing is taking your problem of an infinite series to an improper integral. So knowing how to solve integral and improper integral specifically is a prerequisite for understanding of this test. That's why we teach sequences and series after we teach students integrals, specifically improper integrals. So the problem now lies on testing the convergence of this. If improper integral converges or diverges, the same is going to be the behavior of this series. And if you want to talk about this number n, what is this capital N, where is this coming from? So most of the times what we see is these conditions of being continuous, positive, and decreasing are not true from the very first term of the series. Like first few terms could be like 1 plus 2 plus 3, and maybe after that the series terms start decreasing, 1 over 2, 1 over 2 square, 1 over 2 cube, and so on, something like that. So in that case, you can simply just ignore these finitely many terms. So that's another standard result, that ignoring or adding or deleting finitely many terms do not affect the convergence of the series. They are only going to affect some of the series, but they do not affect the behavior of the series. So that's why it doesn't really matter wherever you start your integral computation from, but by default it starts from that number after which series starts showing that behavior or pattern. So do not worry much about this number, that this has to be very exactly known. Even if you use any other number here, it's not going to change anything, because the important point is being infinite. This controls everything. This really does not control anything. So don't pay much attention to that. So I hope the statement is clear, and now we will apply this to examples and see for ourselves how does this unfold. So usually the questions are longer because you also have to test decreasing, and I'll show you how to test that as well. Right, so let's have an example of integral test. So this is the series given to us, summation n equals to 1 to infinity 1 over square root n plus 1. So consider a function f of x which is 1 over square root x times square root x plus 1. Clearly it's a positive function, it is continuous, and it is decreasing, because these are the three conditions we need, right? Now how to test it is decreasing? Find the derivative f prime x and show that it is negative. Remember it from calculus 1? So finding the derivative of this function, no need to much simplify, just use quotient rule and leave it in the form you get. Convinced that this is negative because everything else is positive, so that will immediately tell you that this is decreasing. Now the job is to solve this integral from 1 to infinity. Now we can use any technique whichever you find comfortable, but here I'm going to use a substitution method to solve this integral. So I'm actually going to substitute square root x plus 1 as u, then du is 1 over 2 root x dx. So you can clearly see dx over root x is sitting over here in your integral as well. So I get the value for that as 2 times du over u. And now it's easy to see the integral is 2 ln u 2 to infinity. You can introduce a variable here for infinity, b, and take the limit b goes to infinity. So this actually goes to infinity. Thus this integral is divergent, or you can say this diverges, and hence your given series also diverges by integral test, because you compared it with an integral and that turned out to be divergent, hence this series also turns out to be divergent. Simple. Let's have another example. So another series we have here is 8 tan inverse n over 1 plus n square. So an is this function. When you rewrite that as f of n, so f of x turns out to be 8 tan inverse x over 1 plus x square. Again, you can see it's a decreasing function. Now fx is positive because tangent inverse x graph looks like this, and your domain is 1 to infinity, so you're looking on the positive side, so it's a positive function. 1 plus x square is of course positive, so the entire function is positive. That means the first condition of being positive is justified. It's continuous because of tan inverse n 1 plus x square, and you find the derivative. Now you will find this turns out to be this. Everything is positive. For it to be negative, this number has to be negative. So that means if you draw the graph of 1 over 2x, it lies below tan inverse x. So 1 over 2x is less than tan inverse x, hence will make this overall quantity negative. So what this will do is 1 over 2x is less than tan inverse x. So 1 is less than 2x times tan inverse x. So making this whole thing negative, making the entire derivative negative. So justifying that this is decreasing function. Now solve the integral. 8 tangent inverse x over 1 plus x squared dx. So I think you might have figured out that tangent inverse x, when substituted by another variable, let's say u, then you will get the same as du. So this is, when x is 1, u is pi over 4. When x is infinity, u is pi over 2. That gives you the new limits. So pi over 4 to pi over 2, 8 times u du. Easy to solve. 8 u square over 2, pi over 4 to pi over 2. And then you can simply plug in the upper and lower limit and simplify that. 4 pi square over 4 minus 4 pi square over 16. This will be 3 pi square over 4. But it's a finite quantity. That means your improper integral is convergent. Hence, your series is also convergent. So you see, for this specific question, integral test was the only option. I'm not saying that happens with all of the questions. For many of the questions, you have two choices. You can use multiple tests, but this kind, you could clearly see the derivative of tangent inverse x function is 1 over 1 plus x square is sitting there. So it's very easy to integrate this function. So that's why, that was the hint that, okay, we can use integral test here. So whenever you see this kind of function, try using integral test and then get your answers. Here we have another example of integral test. Summation n is 2 to infinity ln n over square root n. Now that's your function log x over square root x. You can verify all the things yourself. I'm leaving that for you. I'm just directly doing the integral by making the substitution. Ln x equals to u. So x is e to the power eu, dx is e to the power eu du. This will give you the upper and lower limit as well. When x is 2, u is ln 2. So making these substitutions, square root x will be square root of e to the power u. So u eu by 2 du. Now you can use integration by parts to actually simplify this integral. First function, integral of second minus integral of derivative of first times integral of second. Again, of course, lower and upper limit. So b goes to infinity, 2 b over 2 minus 2 ln 2 e ln 2 over 2. Again, you integrate the second function as well. You'll get the same thing. Now this whole thing will go to infinity because only the middle term is the finite term. Everything else is going to be infinity. So you'll get this sequence, this integral diverges, hence the series is also divergent. So that's all about integral test. And now let's look at another kind of series which is like very frequently occurring and actually very easy to test as well, known as P series. So summation 1 over np, n to the power p. This particular kind of series is known as P series, where P is nothing but a positive real number. Example, very easy to see. You can have summation 1 over n, which we talked about last time. This is a harmonic series. Remember, we introduced this series earlier. 1 over n square, summation 1 over n to the power 4 over 3, 1 over square root n. All of these are P series. Now the result is this series converges if and only if P is strictly greater than 1. So that means if I have n power 1 means harmonic series, this is a divergent series because P is equals to 1. And square is convergent. 1 over n square is convergent. P is 2, which is greater than 1. Square root n again divergent because square root is power 1/2, which is less than 1. So you see, it's very easy to apply and remember this result. So P series convergent only when the power is strictly greater than 1, otherwise always divergent. So remember, we had this example before. At that time we applied nth term divergence test, but we were not able to conclude anything from nth term test because limit of this was going to 0. That's the reason. So, but here now we have another test helping us out in determining the convergence of this particular kind of series. So that's the P series test. Let's see. That's the first example. Summation n is 1 to infinity 3 over square root n. 3 can be taken outside, 1 over square root n, and we just identified 1 over square root n divergent because the power is less than 1. So because of P series test, this is divergent series. Thus, the given series also diverges. Now, this is following from a result which says that constant multiple of any divergent series is also divergent. This is a standard result. Actually, non-zero constant, because if you multiply with 0, it will change everything. Non-zero constant multiple of convergent series is also convergent. So this result is true for both convergent as well as divergent. That means if you have a series, you know its convergence, and then if you multiply it with some number, not n or function of n, any number, then its convergence or divergence remains the same. So that's why whenever you see multiples like 3, 4 or any real number, you can simply take them out and work with the rest of the series and get your answers. So constant multiples do not alter the behavior of the series. Of course, non-zero, because if you multiply anything with 0 times say 1 over square root n, it's actually the 0 series, summation 0, which is a convergent series. We talked about it in the beginning. So originally this was divergent, but multiplying it with 0 changed to convergent. That's why this result requires the constant multiple to be non-zero. All right, that was a simple example. Let's move to next example. 5 over n cube plus 1 over n square, n is 1 to infinity. Now this individually, again, as a whole, it's not a P series. However, as you can see, it's sum of two different P series. It's similar to the kind of question I did for geometric. So now you can break it down as sum of two series. And now first one is definitely convergent because n cube, look at the power is greater than 1. Look at the power here again, the power in the denominator, the power of n, that's greater than 1. So this is again convergent, and we already looked at the result that sum of two convergent series is always convergent. So that's like a repetition of the result we already used. So now you'll remember it. Hence, the given series is also convergent. So you can actually have no other result that sum of one convergent and one divergent series is divergent. And the third result is sum of two divergent series is anything. It can be convergent or it can be divergent. It may be convergent or may be divergent. So you cannot say anything. So it's easy to understand this from the analogy that if you add two finite numbers, so finite number plus finite is definitely finite. finite number plus infinite is definitely infinite, but if you have infinite plus infinite or infinite minus infinite, then you cannot say anything. So actually the sum is a general term. It could also mean difference, sum or difference. So when it is infinity minus infinity, in that case we are not sure whether the sum is going to be convergent or divergent. So these are some additional results. If you know them, it's easy to apply them to questions and solve complicated examples wherever you have expressions like this. So convergent plus convergent is convergent. Convergent plus divergent is divergent. But divergent plus divergent may be anything, could be anything. Another example for P series. So an is 1 over square root n. Now this series clearly is divergent. Now here we have another example, bn, which is 1 over n square minus 1 over square root n. Again, bn is further the sum of two series. Bn is divergent because 1 over n square is convergent, while 1 over square root n is divergent. We just learned one convergent, one divergent, added or subtracted gives you divergent. Now if you consider third series Cn, which is an plus bn, so you can see summation Cn is summation 1 over square root n plus 1 over n square minus 1 over square root n, cancels out, leaves you with 1 over n square, which is convergent. So this example demonstrates that divergent plus divergent can be convergent. But it doesn't happen always. There could be different kind of examples where divergent plus divergent is also divergent, right? So this example was specifically constructed to demonstrate this behavior to you. And yeah, so you can apply this to other examples as well. So that's all about P series. And now we are going to begin with comparison test. Actually, comparison test has two versions, direct comparison test and limit comparison test. I'm only going to cover the limit comparison test here because that's like sufficient to cover like a lot of examples. So let's get started. So let's first know the statement of limit comparison test. So clear from the name, we need a comparison between two series. So suppose an is a positive term series and bn be another positive term series, and capital N has the same meaning, it's an integer. Now if limit n goes to infinity, an over bn turns out to be a positive number, then the test says these both series behave alike, means they converge and diverge together. Means if one converges, other converges. If other converges, the other diverges. Like so, they do it together. The behavior is same. Second condition, if limit n goes to infinity, an over bn is 0, and the bn converges, then you can say an also converges. The third condition is if limit n goes to infinity, an over bn is infinity or does not exist, and bn diverges, then you can say an also diverges. So you see, that's a big statement to understand. Let me break it down for you. So you have original series, summation an given to you, for which you are actually interested in finding out whether it's convergent or not. So you choose another series bn for comparison, whose convergence is something which is already known to you, or it's relatively easier to find convergence of bn. So usually bn is like a known series, and most of the common choices for bn is the P series, because P series fall into a category for which like we immediately know the answer, whether that's convergent or divergent. You can also use geometric series for comparison, but most of the examples use P series for comparison. So now how do you then compare? So you take this ratio an over bn and then compute the limit n goes to infinity, and depending upon what it turns out to be, you make the conclusion. So the first conclusion is always like the most preferred one. Everybody is willing for, okay, it turns out to be a positive constant. Because if it is positive, then you know the immediate simplest conclusion is, okay, they behave alike. Whatever is behavior of bn, the same is behavior of an. But the second conclusion is, if it doesn't turn out to be positive, but actually turns out to be 0. Now, based on that information, you cannot say anything. Along with that, this condition should also satisfy. That means the series which you chose for comparison needs to be convergent. So 0 and convergent makes a combination. And then you can conclude that an converges. Similarly, infinity and divergent has a combination. Then you can conclude the given series diverges. Suppose in some example your limit turns out to be 0 but bn is divergent, so 0 and divergent, if this combination appears, then this combination does not work, and vice versa. That your limit does not exist and bn is convergent. So that means in that case, when this kind of situation happens, you have to change the series for comparison and redo the test or use some other test. So enough with the statement. Let's apply this to the examples. So the first example we have here is 2 to infinity 2n over n square minus n plus 1. Now an is this series. I'm going to choose bn as n over n square. I'll explain you the reason later. Limit n goes to infinity, an divided by bn. So you take the ratio of both of these expressions. 1 over n divided with equivalent to multiplying with n, and then simplify the limit to 2n times n gives you 2n square minus n plus 1. Simplifying, you will get 2. The limit is actually 2 when you divide with n square. So positive constant. So that means it's the first case, and the conclusion is summation a and summation bn behave alike. Means they converge or diverge together. Now look at bn. bn is harmonic series, right? Summation 1 over n, p series, which is actually divergent because p is equals to 1. So therefore, the given series is also divergent. An also diverges. So that's the demonstration of comparison test, limit comparison test. But the bigger point is, how do you know that you have to choose this bn? How to choose bn so that it works? Because if you choose a wrong bn, it may not be giving you any meaningful conclusions. So the simplest way to choose bn accurately is look at the behavior of your series. Because we are choosing a series for comparison, so that means we are trying to see how does my series behave when n is very, very large. So that means you try to see the dominating term. So in the numerator, there is only one term. So the highest power is the dominating power, n to the power 1. So that's why I choose n to the power 1 in the numerator. And in the denominator, it is the biggest power term, n square. So that's why I chose n square as the denominator. When you simplify that, you will get 1 over n. So choose the largest power in the numerator divided by the largest power in the denominator. Simplify, you will get your bn. And once you get your bn, simplify, follow the test and all the steps, you will get your answer. And this technique of choosing bn works in most of the examples. Let's have another example. Summation n is 1 to infinity n plus 2 to the power n over n square times 2 to the power n. So that's my an. So I'm going to choose bn on the basis of that when n is large, how my series behaves. So 2n is very, very greater than n. So bn is 2 to the power n over n square times 2 to the power n, which is 1 over n square. Limit n goes to infinity, an over bn. Now again, you rewrite both the an and bn here and simplify this limit. I told you in the beginning, you should be good at simplifying these limits. n square gets cancelled out, and eventually I'm left with n over 2n plus 1. Now this thing is definitely going to 0 because 2 to the power n is very, very big than n when n is large. You can clearly see 2 to the power is greater than 1, 2 to the power 2 is greater than 2, 2 to the power 3 is greater than 3, and so on. It keeps increasing. So the limit is 1. First case, so that means both the series behave alike. Now look at your Bn. Bn is convergent because that's 1 over n square. Therefore, the given series also converges. Let's move to next example. 1 to infinity ln n over n 3 to power 2. Now for this kind of question, there's a clever technique of choosing Bn. So whenever you have ln n in the numerator and n to the power something greater than 1 in the denominator, this is how you choose it. So choose Bn is 1 over n to the power p, where p is something less than 3 by 2 but greater than 1. Now 3 over 2 is the power which is original power in your question in the denominator. So an is that. Now Bn is, I'm going to choose 1.1 because that lies between 1 and 1.5, right? Now when you take the ratio, you actually get ln n over n 3 over 2 and 1.1. Simplify. 1.5 minus 1.1 give you 0.4. Infinity over infinity, indeterminate. Use L'Hopital's rule. 1 over n in the numerator. Use power formula in the denominator. Again simplify. So you'll get 1 over 0.4 n raised to power 0.4, which is 0. So thus an is convergent because the limit goes to 0, and Bn is convergent because Bn was 1.1. It's a p series, right? So you remember this technique of choosing Bn in this case, you will always get this question done. You have to choose Bn as a p series, but you do not know what should be p. So this is the formula I'm telling you. So whenever you have a series of the type ln n divided by n to the power something which is greater than 1, then take that number and choose a p which lies between 1 and that number. Now this was 1.5. So there are infinitely many numbers between 1 and 1.5. In this case, I chose 1.1. Any other would have worked. You could choose 1.2, 1.25. Anything would have worked, right? And following all the same steps, you'll always get answer convergent. So it's a clever way. This technique is not explained anywhere in any of the textbook. This is something I invented myself after observing patterns of doing so many questions, that every time if I take Bn in this technique, it always works. So it's like along with the techniques, along with step-by-step techniques, you should also be good at identifying patterns so that you can make decisions like this. So this is extremely helpful. Try this on this kind of examples as well. Now we have another example for comparison test. Summation 2 to infinity, ln n this time, but square root n. So in this case, I'm going to choose Bn, which is same as the denominator power, n to the power half. Now I cannot choose Bn using the previous technique because the power is already less than 1. So I can't choose anything which is greater than 1. I have to take the same power. So in this case, if you apply limit n goes to infinity, an over bn, it's simply ln n because you choose it exactly same, that gets cancelled out, it goes to infinity. And bn is obviously divergent because the power is less than 1. P series test tells you that this is divergent. So you see infinity and divergent combination gives you that your original given series also diverges. So you see, if you compare this example with the previous example you had sorry. The previous example, you had ln n over 3 over 2. In this example, you had ln n over n 1 over 2. So when the power is less than 1, in that case, choose bn exactly same as that power. If the power is greater than 1, then choose bn between 1 and that number. Choose bn as 1 over n to the power p, where p lies between these two values. So this works. This covers like a lot of questions. So that was all about comparison test. So finally, we are left with two more tests to cover up: ratio test and root test. So let's see what's the statement of ratio test. Let an be a positive term series, and suppose limit n goes to infinity, an plus 1 over an is rho. Now if rho is less than 1, then the series converges. Series diverges if rho is greater than 1 and the test fails. The series may converge or may diverge if rho is exactly equals to 1, or you can say test is inconclusive if rho is exactly equals to 1. So in this case, you're also taking the ratio. You are also taking the ratio in the comparison test, but that was called a comparison test because you were using an external series. You were relying on a different series to give you the answer. But here, you are taking ratio of the terms of the series itself. You do not rely on any bn. You're only taking nth term and n plus 1th term and taking their ratios. So let's see how we do that in examples. 2n factorial over n factorial. Hint. So whenever you have factorials in your question, always use ratio test. Always. Because you will see how remarkably it is going to help you simplify. So rewrite an. Now change n to n plus 1 and write an plus 1. So actually it should be 2n plus 2. And now take the ratio of an plus 1 with an. So when you do that, so you see a lot of factorials into the ratio. So you need to simplify, expand the bigger factorial. So 2n plus 2 will be 2n plus 2, 2n plus 1 times 2n. N plus 1 will be n plus 1 times n factorial. Alright, let's apply ratio test onto our very first example. Summation n is 1 to infinity 2n factorial divided by n factorial. So that is the hint, that is the recognition. The moment you see factorials present, always use ratio test. It's going to do wonderful job on simplifying your an. So use ratio test in this case. So I'm going to rewrite an as 2n factorial divided by n factorial times n factorial. Change n to n plus 1, 2n plus 1 factorial, n plus 1 factorial, n plus 1 factorial. Actually, it's 2n plus 2 because 2 times n plus 1 would give you that. Now take the ratio. An plus 1 divided by an, and then take limit n goes to infinity. So of course limit is going to be evaluated in the end. First you have to simplify the expression. Divided by an, and now multiplying with the reciprocal of an. Keep an plus 1 same, multiply with the reciprocal of an to simplify this. And now technique to handle factorial is expand the bigger one. So 2n plus 2 factorial will be 2n plus 2 times 2n plus 1 times 2n factorial. N plus 1 times n factorial, n plus 1 times n factorial. And do not change anything about it. You see these getting cancelled out. And now you are left with 2n plus 2, 2n plus 1 over n plus 1, n plus 1. An expression free from factorials. Very easy to simplify now. You have done these kind of limits before. Divide with n in all the terms. So you will see you get 4, which is greater than 1. does this series diverges? Because the test was about comparing the ratio with 1. If it is less than 1, then convergent, greater than 1, then divergent. So since this is greater than 1, so this is divergent. So how did you find this example? So give it a try yourself without looking at the solution, then you will understand. It needs a lot of practice to do these kind of questions. Another example, summation n is 1 to infinity n factorial times e to the power negative n. I'm going to rewrite that as divided by e to the power n. Now my an is n factorial over e to the power n. So an plus 1 is n plus 1 factorial divided by e to the power n plus 1. Now if you compute limit n goes to infinity, an plus 1 over an, and now you simplify in a similar way, the way we did in the previous question. This is actually simpler than that. N plus 1 factorial divided by e to the power n plus 1 multiplied by e to the power n over n factorial. Now expand n plus 1 factorial. N plus 1 times n factorial and e to the power n plus 1, e to the power n by n factorial. This gets cancelled and you are left with only n plus 1 and divide by e, because you can use the rules of exponent to simplify it. Now of course it goes to infinity, so this is again divergent. So anything which is greater than 1, so infinity is also greater than 1, so divergent. Let's have another example of ratio test. 1 to infinity, 1, 3, 2n minus 1, 4 to the power n, 2 to the power n times n factorial. So the numerator is actually product of so many numbers, odd numbers. You can see that, right? 1 times 3 times 5 all the way up to 2n minus 1. Now this is an. I'm rewriting it. Now an plus 1 is going to be same product, but in the end it will go up to 2n plus 1 because the next odd number in the list is going to be 2n plus 1. 4n plus 1, 2n plus 1, n plus 1 factorial. That's the tricky part. You have to pay attention why it's 2n plus 1, because when you replace n plus 1 with the last term, you get 2n plus 2 minus 1, which is 2n plus 1. Take care of that when you compute the next term in the product sequence. Limit n goes to infinity, an plus 1 over an. So rewrite everything, take the ratio. 2n plus 1 divided by 4n plus 1, 2n plus 1, n plus 1 factorial times 4 to the power n, 2 to the power n, n factorial, and so on. Now you see these getting cancelled out and you're left with 2n plus 1 over 4 times 2 times n plus 1. Because n plus 1 factorial will be expanded as n plus 1 times n factorial, and these will be expanded like this, so you can see these getting cancelled out. So finally you are left with 2 plus 1 over n, 8 times 1 plus 1 over n, which is 2 over 8, which is 1 over 4, which is less than 1. Hence, the given series is convergent, because the ratio turned out to be less than 1. So these are very typical kind of questions for ratio tests. Like these questions cannot be easily done using any other test. You try an nth term test, you won't succeed. You try telescoping series, you won't succeed at all. Integral is too difficult with factorials because they are not continuous kind of functions and they are not P series. So all of those factors eliminate the possibility of using those tests, making it suitable for ratio test. So that's why you will notice the specific kind of complicated questions very easily done using ratio test. Another example for ratio test we have here. Summation n is 1 to infinity, n to the power 10 over 10 to the power n. Now when you change n to n plus 1, this is what you get. And now take the limit n goes to infinity, an plus 1 over an, n plus 1 raised to the power 10 over 10 to the power n plus 1 times it. And now simplify. There will be 1 extra 10 in the denominator. And now 1 plus 1 over n to the power 10. This is of course less than 1, so this is convergent. Because you can clearly see this part is simply 1, because n goes to infinity, this will go to 0, 1 plus 0 is 1, 1 to the power 10 is 1, so 1 over 10 times 1 is 1 over 10. So this is convergent because this is less than 1. So this example was included to demonstrate that it's not always the complicated factorials kind of questions can be done using the ratio test. Questions like this can also be done using ratio test. So that was all for ratio test. And finally, now we are moving towards our next test, which is the last test for this video lecture, root test. This is also known as nth root test. So let's have a look at the statement. Let an be a positive term series, and suppose limit n goes to infinity, an to the power 1 over n is rho. Then the series converges if rho is less than 1. The series diverges if rho is greater than 1 or infinity. And the third is series may or may not converge, means the test inconclusive, the test fails if rho is equals to 1. So you can clearly see here that the conditions of convergence for root test are exactly same as the conditions of convergence for ratio test, right? But the difference is there you were taking the ratio of an plus 1 and then computing the limit, but here instead of taking a ratio you are taking nth root, right? Nth root is coming from like the way you take square root, cube root, 1 over 2, 1 over 3 in the power. So 1 over n in the power is a symbol of taking nth root. So that's why the name of the test is root test. Now, what kind of examples does we apply root test to? So the very first example we have here is n square over 2 to the power n. Now when you apply root test here, take the power 1 over n of the whole thing and then take limit n goes to infinity. Simplify, you will get n to the power 1 over n square of that. In the denominator you simply get 2, which is 1 over 2. Why this is 1 over 2? Because you see the numerator is the standard limit we have talked about before. So that's why this is convergent series, because 1 over 2 is less than 1. So you see how knowing that standard limit helped here. That limit n goes to infinity, n to the power 1 over n equals to 1. And this is actually many of the times used in almost like a lot of examples in the root test. This particular standard limit keeps appearing frequently. Let's have another example for root test. Summation n is 1 to infinity, 5 to the power n over 3 to the power n. So it's actually 5 over 3 to the power whole of n. When you take the power 1 over n of the whole thing, it's simply 5 over 3. Now if you take limit n goes to infinity for the same, it's greater than 1. So thus by root test, this series obviously diverge. Alternatively, if you might have noticed, this series is actually a geometric series. So since this is a geometric series, you can also use geometric series test. Now multiplier is greater than 1. So greater than 1 means divergent. So thus you are getting divergent even from the geometric series test. That's going to happen. So this example has been included to tell you that there can be multiple tests used on the same example depending on what clicks you. Sometimes one of them works, sometimes both of them works. But yeah, whichever works for you, works for you. You do not need to show the validation with some other test. But here we could see, okay, it can also be done using GP series, so we did that. And of course, if a question can be done multiple ways, whichever way you use, the final answer has to be same. That cannot change. So heading over to the next example, the second last example of today's lecture, 39. Summation n is 2 to infinity n over ln n to the power n. So n is coming in the power. To balance that, we will take the nth root. So this will give you n to the power 1 over n ln n to the power n times 1 over n. And when you take now limit n goes to infinity, it's simply n to the power 1 over n over ln n. Now we just saw the numerator limit is 1, again the same standard limit. It's 1 over ln n, which goes to 0, which is less than 1, hence convergent, because anything less than 1 gives you convergent. So if you have noticed the pattern, what kind of examples we are applying root test to? All of these examples had something in common, n present in the power. Because to get rid of that n in the power, we are raising it to the power 1 over n. And so that n and n gets cancelled and we get something free from the power n. Because the variable sitting in the power means infinity in the power is always a problematic situation to handle. So we want to get rid of that. That's why we are using root test. So that's the kind of questions you use root test. The moment you spot n sitting in the power, use root test or try. And now we are heading towards the last question of this today's video lecture, example number 40, to be done using root test. So that's the series given to me, negative 3 to the power 2n plus 1 over 2 to the power 5n minus 1. So if you notice, this is not a positive term series because of the presence of negative 3. But we can do something to get rid of that minus. So notice that you can rewrite minus 3 to the power 2n plus 1 as minus outside and then only 3 to the power 2n plus 1. Because 2n plus 1 is going to be an odd number. So negative 1 raised to the power 2n plus 1 is minus 1. So that's why you can pull that negative outside. So I can write an as minus bn, where bn is free from negative sign. Now bn is a positive term series, so I'm going to use root test on bn, not on an. So for bn to the power 1 over n, this is what you get when you raise bn to the power 1 over n. Divide the power by n and now take the limit n goes to infinity, bn to the power 1 over n. You will get 3 to the power 2 plus 1 over n divided by 2 to the power 5, which is 9 over 32 less than 1. Thus bn is convergent. So what happened to an? Now an is simply a constant multiple of bn. So an is also convergent. Remember we had that result? Non-zero constant multiple of a series is also convergent. Like multiplying with a non-zero constant does not alter the behavior of the series. So if bn is convergent, an is also convergent. So non-zero constant multiple of any series does not change its behavior. That's a reiteration of the same result we talked about before. So you see, the given series was not a positive term series, so you could simply give up and you could simply say, okay, maybe we cannot use any of the tests we just discussed because all these integral, ratio, comparison, root tests, they are only meant for positive term series. But a clever observation made your series into a negative term series, that your series is actually a negative term series. So you can pull out the negative from all the terms and check the convergence of only the positive part. This is how you do it. That is why there is no separate category for negative term series, because negative term series is essentially a constant multiple of positive term series. So that's why you're only taught to test the convergence of positive term series, because negative does not really change anything. It's only going to change the sum of the series, which we are not finding here in these kind of examples. So that's all for today. We will be continuing with part 4 and part 5, which is alternating series and power series, in part 2 of this video lecture. So I'm going to upload that very soon. So thank you for watching today. Hope you understand a lot of things. So yeah, see you soon.